Maths educational video. This video is about a very important and useful result in vector calculus known as the Green Theorem. Named after the famous scientist George Green. Roughly speaking, Green's theorem relates a line integral to an area integral, a double integral over an area. Before I look at the full statement of the Green's theorem, let us lay out some groundwork. First, the line integral part. Green's theorem is for two-dimensional vector field. So let's consider two-dimensional line integral. The one in the box is the formula we already know. What we're going to do is to replace the dot product with the expression involving the individual components. So for example, f shall be replaced with p and q, the component functions. And r prime will be replaced with x prime and y prime. That can be done by working out the dot product. That will give us the expression in the last line. And now we introduce a notation commonly used, and it also appears in the statement for Green's theorem. This quantity in terms of the variable t can be written in short as the line integral over c of p dx plus q dy. The one in the blue box. So we call this line integral notation in component form. Although we do not do Green's theorem in 3 dimensions, but here is just a generalization of what we just discussed. For the case of 3-dimensional vector fields, where you have p, q, r as the component functions, and the parametric equations for c are x, y, and z, t respectively, for the I, j, k components, then the line integral of f over c has a corresponding component form, the one in the blue box. Another concept we need before we discuss the Green's theorem is the concept of orientation of a curve. Green's theorem deals with closed curve. So first let's talk about the concept of a simple closed curve. A closed curve is simple if it does not cross itself. So this is just an example of a curve that is closed but not simple, simply because it crosses itself at this point. Next, the orientation of a curve. When we say a curve is positively oriented or it has a positive orientation, what we mean is this. If RT is the parametric representation of the curve, then as t increases, the point should be moving along the curve in the anti-clockwise sense. So that we call positive orientation. So here are some more examples of positively oriented curves. The two curves on the upper part of the diagram, and negatively oriented curves, those below. Following the arrow, you know positive orientation is for an anti-clockwise traversal, negative orientation for clockwise movement. Now, the Green's theorem. As I mentioned earlier, this is a two-dimensional result. We take a two-dimensional vector field pi plus qj. We take a region enclosed by a closed simple curve C. And the orientation has to be positive. Furthermore, the component functions for f must be functions with continuous partial derivatives. Continuity of partial derivatives is to ensure that this term on the right makes sense. So these are just some technical conditions. So under all these conditions, the line integral on the left, we now know this notation p dx plus q dy, what we just discussed at the beginning of the video, is numerically equal to the integral on the right. And this is not a line integral, this is the usual double integral, iterated integral that we learned before. Just a quick remark on orientation. If the curve C is known to be negatively oriented, the question now is, can we still apply the Green's theorem? The answer is yes, provided you put a negative sign. Negative to account for the negative orientation. So this is something we have to keep in mind. So when dealing with questions involving the use of the Green Theorem, do check that the curve C is positively oriented. If it is not, you need a minus sign. We end the video with two numerical examples on the Green Theorem. Example 1, we are asked to find this line integral for a closed curve. Now this notation with a circle on the integral sign tells us that curve C is closed. Indeed, based on the description, we can tell that C is a closed curve. In fact, we can plot it from the origin to 1, 0. So that is the one I'm highlighting here. And then 1, 0 to 0, 1. So along this line. And finally, 0, 1 back to the origin. Not only do we know this is a closed curve, we also know that the orientation is positive because we are moving in the anti-clockwise direction. So we are now ready to apply the Green's theorem. But just a quick remark. The question doesn't suggest that you have to use the Green's theorem. However, the use of the Green's theorem is something wise to do. And that's because this particular line integral actually involves 3 lines. So you expect 3 integrations to do. But if you apply the Green's theorem, all you have to do is to compute one double integral. So it saves a lot of time. We're going to apply the Green's theorem faithfully, working out the integrand dq dx minus dp dy based on the pq that we are given. It turns out that the integrand is just equal to y. Furthermore, this region D is a type 1 region. I leave it to you to check that it's also a type 2 region. But we will use the type 1 region for the computation. X lies between 0 and 1. Y lies between 0, the x-axis, and the slanted line, which is given by the equation y equals to 1 minus x. So this integral, this double integral can be written in the iterated form, which can be easily computed. Answer 1 over 6. Another example, this time we have to use the polar coordinates. But first we inspect the question. Again, it's a closed curve, positively oriented circle. So we know the Green's theorem is applicable. And if you apply the Green's theorem, you immediately see the advantage of doing so. The integrand dq dx minus dp dy turns out to be something simple. It turns out to be x squared plus y squared. So you see that in the original question, there are many terms. We have 4 functions, e4x, y cubed, cosine 3y, and x cubed. But after applying the Green's theorem, 2 of them disappeared, leaving us with projective terms. So that's one advantage of the Green's theorem. Now let's look at the region. Because we have a circle, we can try polar coordinates. Polar coordinates is ideal for situations like this, and the region is circular in nature. Here we recall formulas from polar coordinates. Applying the formulas in the box together with x squared plus y squared equals to r squared in polar coordinates, the integral can be written in terms of r and theta. We end up with the double integral of r cubed dr d theta. And that can be found easily. Final answer is 1.5 pi. And we are done.